Hey guys, in this video, we're going to walk through this Leetcode number 7, reverse integer. So we are given a signed 32-bit integer x, and we need to return x with the digit reversed. And if that cause the value goes overflow, so it goes outside the range of negative 2 to the power 31 and this range. So this is the range for 32-bit integer range. If that's go outside that range, we gotta return a 0. Also, there's an assumption here that's not allowed to store the 64 bits. Anyway, so let's look at this example here. If we are given an integer 1, 2, 3, so that should be 123, and that's reversed to 3, 2, 1. If that was a negative 1, 2, 3, and the returning should be negative 3, 2, 1. And if that's 120, 1, 2, 0, so the reverse would be 0 to 1, but the 0 numbers drop, right? So this is integer. And the last example, this is a trivial case. 0, the reverse is just will be itself. And this question was kind of popular, but that's more unlike than like. So anyway, so it was asked by Amazon, Apple, Adobe, Google, Facebook, Microsoft, Bloomberg, eBay, and American Express. So I'm going to solve this problem in two approaches. So whenever I see reverse, the first thing come to my mind will be reversing a string, right? And maybe we can utilize some of that. Let me walk you through how can I do that. So we will do it in two cases. One, if this is a negative number, and if that's the case, we just put a negative sign in front of it, and then that forces it to be a positive number. And then we convert that absolute value, because if that's integer, that's the positive just itself. If that's negative, it will be times negative 1. So it will be absolute value, and then we convert it to a string by using this string operation, and then we can just reverse that string. In Python, we can do that very easily, and then we convert it back to an integer by using the int function in Python. If that was a negative number originally, we just put a negative sign in front of it. Otherwise, you should put it back to the integer. And also, there was a condition where it does not allow us to go overflow. And so we compare the number. If that negative number is within the boundary, and then just return the number itself. Otherwise, you return a 0. That means it's go overflow. On the positive sign, if the positive sign is smaller than the biggest number for the 32 bits, and then just return that number. Otherwise, it's return 0, in which case it's go overflow. And this is going to work. See, this number changes, but looks pretty efficient to me. So for time complexity, it is big O of log x. So log x is basically the number of integers in x, and for space complexity is big O of 1. So basically, it's a time complexity is a big O of a number of integers, not number of integers, number of digits, and that mostly comes from this guy over here when we reversing it. And the interviewer might not be happy about this approach. This is a little bit clever because we utilize a lot of internal functions. Also, we convert back to a string, but it works, right? And then now I'm gonna walk through a second approach that might be something that the interviewer might ask. I have a follow-up question if we first use this approach. So let's look at this example in here. I think this walk through the algorithm that I'm gonna put in on the code. So the first example we have was 1, 2, 3. So 123 is equal to 120 plus 3. So the gist here is we need to get the 3, also 120. So 120 is equal to 12 times 10, right? And then what we can do is take the floor division. So 1, 2, 3, and floor divided by 10, and then we get 12, right? And then we can get exactly this part. And then the modular of 10 will be 3, and that's the current digit. That's the first digit we need to put it in the front in the answer. So we save that, and then now we have the 12, which will become the current x. So the original x is 1, 2, 3, and now the current x will be 12. And then we take the floor division again, and that will come back to as 1. And that will be the x again. That will be the x that we'll be working with. And then we take the 12, take the modular of 10 again, and that we can extract the second digit we need, which is 2. And in that case, now what we have is what we can do was have the original digit times 10 plus the current digit. So it will have a 32. So this is fairly close to the required answer, which is 321. And at least we get these two digits nailed down, and also in the kind of in the correct position. But we are still missing one digit at the end. And what we can do is what is left is the 1, which has been assigned to the next x, and 1 take the floor division of 10, that will be 0. So the next digit right now, the next x right now is going to be 0, and this is the condition where we can end up in some sort of for loop or while loop, right? Because the current x is already 0. And the current digit right now, originally the current digit is 2, and now we take the modular of that. So the current digit right now is 1. So now it's finished, because the answer that we had before is 32, and now we times 10 and plus the current digit. So each time when we have a for loop inside, we plus the 10 in the original answer and then push everything to the front. So 321, that's exactly the answer that we need. So let's put that in the code. And same as before, we have to convert the x to be the positive side if that was a negative number. That's exactly the same chunk that we had before. And now to get us started, and we have the current digit, so we take the modular of 10, and so in this case it was 3, right? So we extract the current digit, which is the first digit. We take the floor division out of 10, so that's will be the next x. So we assign it to the next x, the current x. So we go from 1, 2, 3, take the floor division of 10, so it will be 12 in this case. And the answer right now is the current digit, which is 3, while the x is greater than 0. And we do that until x is equal to 0. And then this whole thing will stop, because remember there was a condition where this is where we can stop. Okay, and this is exactly the condition that we put it on. So the current digit, so the next current digit is gonna be the x, which right now is 12. Take the modular of 10, so it's gonna be 2 in this case, and then we push what we had before, which was 3 times 10 plus 2, which we have 32 in the current answer, and then we take a floor division, so 12 and 4 divided by 10, which is in 1 in this case, and 1 is greater than 0. So the current digit right now is 1 modular of 10, which is 1. So we add that to the answer and then push our existing answer to the left by multiplying by 10. So right now is 3 to 1 in this case, and x right now is 1. Floor division by 10, which is 0, and 0 is not greater than 0. which finishes the entire while loop. And yeah, so this is so much for the ball part of the main part of it. And also we have some checking to make sure that it does not go overflow. And this is exactly what we just discussed. And yeah, this is gonna work as well. This is so much for my solution. For the time complexity, it's basically the same time complexity we discussed before. It's big O of the number of digit. Also the space complexity. We need a current digit to keep track of things and answer. So it's gonna be big O of log x as well. Yeah, so not big O of log x is gonna be big O of 1. Sorry, because we only have one digit actually, one number. Yeah, so this is so much for my solution. I hope you like it. If you do, please like this video and consider subscribe to the channel. That will be huge encouragement. Hopefully I will see you in the next video. Thank you for watching.